Okay, so let's start the first lecture of the semester. As it was indicated in the syllabus, we'll start by a review session of the topics that you learned in your previous quantum mechanics course. This is intended as basically a summary of that material or some sort of intention to focus on the things that will be useful from the previous course in this one. So try to not lose yourself in the forest. And I'll start the lecture now by sharing my screen. Okay, so this is the first lecture of our course related to a review session as indicated here. So what we will focus on is basically on inner product of two vectors in the Hilbert space, matrix representations of Dirac Ketambra vectors and operators, outer product of vectors, position and momentum operators in position and momentum representations, and the Schrodinger equation in these representations. So of course, I'm just assuming the background of your previous course. Most of these won't be new. I'm just trying to kind of like get to the essentials of what you learned or part of what you learned in your previous course. So look, quantum mechanics was born from the realization that classical physics could now describe several experiments in which the measurement outcome was discrete rather than continuous, which was expected from the previous classical physics. So this rendered basically in Schrodinger's equation, which is one of different formulations of quantum mechanics. And Schrodinger's equation is a description of this new quantum physics in terms of eigenvalue problems because the experimental outcomes were discrete. And then you find a natural language in which to model these experimental findings as a set of discrete eigenvalues. That's why, in a way, this kind of PDE is important for the description of the findings of quantum mechanics. And therefore, because of this, the natural space, if you want abstractly, for quantum mechanics, given that you have these formulations such as Schrodinger's equation, which encompasses the experimental outcomes as discrete eigenvalues, is precisely one of eigenvalue problems in PDEs. And so the spaces that happen in eigenvalue problems in PDEs are Hilbert spaces, which are vector spaces, which can be maybe or may not be infinite dimensional, but they are complete vector spaces with their inner product. The inner product lets you establish angles between vectors. That's the interesting part, and particularly the concept of orthogonality. So the field of mathematics related to the study of Hilbert spaces is function analysis. Loosely speaking, is some sort of linear algebra for infinite dimensional spaces. So I'm trying to make an analogy or a connection with something that you already know. And in our case, the points in their space, which we will be calling vectors, they are functions instead of components, right? So that's the difference. Before, you might be familiar, of course, with linear algebra, which has vectors, and essentially is something like this. You have n components, discrete, right? The difference is that now somehow the index is continuous. So you have a function where, well, it's a function of x where x is a real index instead of having discrete x1, x2, xn, etc. So that's the analogy and how we will pass, say, from the discrete case to the continuous case when we talk of functions rather than vectors with a finite set of components. So again, the number of components of our vectors is not finite anymore, but they have the cardinality of the real numbers. So just to make some analogy. Well, what about the inner product of the vectors in the Hilbert space? Okay, so here we are going to start a little bit abstractly, but you are familiar with this from the previous course in quantum mechanics. So it will help you to perhaps understand in a more mathematical way what you did last time. So let's say that you have a vector space that we're going to call H. And then let's say that you have an inner product, which is a mapping or a function, which is basically taking two elements of the Hilbert space and then taking them to the field of the complex numbers. But this inner product mapping should satisfy some properties. The properties are is that this mapping is linear in the second argument. So let's say you have elements f, g, h from the space H, and then you have two constants which are complex. Then, because we said that it's linear in the second argument, if you have H inner product with alpha f plus beta g, since the linearity is in the second argument, you can take out constants and you can split the sum, such as this. The second property is that this mapping should be conjugate symmetric. What do we mean by this? Is like if you have two elements fg in this space H, then if you compare the inner product of f with g, then it's the complex conjugate of the inner product of g with f, right? So we have two equivalent notations for the complex conjugate of a complex number, which is the bar or the star, okay? So these are both notations for the complex conjugate of g dot f. So the third property is that if you take inner product of a vector with itself, you get a non-negative result. So it's greater or equal to 0 for any vector in the space H. And most importantly, if the result is 0 of this inner product with itself, that can only happen if f is equal to 0, okay? So the type of mapping that I just described is called sesquilinear. So again, with these properties. And just as a heads up, if you were to consult math textbook in functional analysis, the notation is a little bit different. It's not so important right now, but just for your general culture. So for mathematicians, they may change or attribute the linearity to the first argument, and they might denote the inner product in terms of parentheses rather than the sorts of brackets that they have. Anyways, Hilbert space is a vector space as we described with an inner product, but we need one more condition, and that condition is called completeness. So before we go into detail into what this means, we need to define or notice that the inner product can induce a norm, such as this, right? So if you take the square root of the inner product with itself, you have a norm for each element in Hilbert space. And with the norm, you can define a distance between elements via the norm of the difference, right? So if you want the difference between f and g, you can define a distance by the norm of f minus g. Now, let's say that you study sequences of points in this abstract Hilbert space, right? So you have an element, well, an infinite set of vectors. And you notice that this property holds, which is that if you go to the limit as you approach infinity for the distances of points far away, essentially fn minus fm normed, and then the limit, and the limit as both n and m go to infinity, then this is 0. This is a sequence that is called Cauchy sequence if it has this property. If that sequence has this property, then the space is called complete if every one of these types of sequences converges to a vector f in the Hilbert space. That might not happen, but if this happens, then the space is complete. And that is the extra condition that you need to have a Hilbert space, is the three properties above mentioned plus completeness. So if that's the case, the vector space is complete and by definition a Hilbert space. Okay, so now the Hilbert space will be the set of possibly complex valued square integral functions over the given interval AB. So this is the kind of Hilbert space that we will focus on, okay? Basically functions over an interval. We'll define the interval according to the problem. It might have to do with the domain if you are in the position space. We'll clarify that in a second, but for the moment, follow that. These are the particular kinds of elements in the Hilbert space that we will care about. So what do we mean by square integral functions? So those are functions for which if you take basically the integral over this interval of its norm squared, which is the integral over this interval of the function multiplied by its conjugate, then this is not infinite, okay? This is clearly greater or equal to 0 because the argument is, well, basically the squared norm, even if it was complex, but it cannot blow up, it cannot be infinite. And that's what we call square integral functions. And there's a notation for this Hilbert space, which is L2 over the interval AB. And we can induce a norm, again, by defining as the norm the square root of the inner product with itself. And just using this particular definition of the inner product, well, you see that if you take the inner product with itself, you have integral of f star f, which is the same thing that we had before. So we're basically asking that the norm, the way it's defined, it's not infinite for our elements. And okay, to clarify what is the inner product that we are using for our space of square integral functions, we have the inner product of f with g is the integral from a to b of f star of x, so the conjugate of f, times g of x dx. And well, if you remember your classes on calculus and integration, this integral is simply the limit. So it's the limit as you decrease the number of intervals in your partition of f star evaluated at a point inside the partition or inside of each one of the intervals considered, xi, gxi, and then the length of each interval. So it might sound unnecessary of why I'm saying this, but the reason I'm writing the definition of the integral is just because I want to make the parallel with the way the usual norm of vectors or inner product of vectors is defined, right? So anyways, in the definition of integration, you have a regular partition of the interval AB. And again, the objective of writing this extra thing is to make clear how the inner product in L2 over AB is basically an infinite dimensional extension of the usual inner product of vectors. So hopefully that will be illuminating in terms of how we pass from the finite Hilbert spaces to the infinite dimensional Hilbert spaces. So there is a very famous inequality, which is called Kochizwar's inequality, which tells you that the norm, or yeah, I guess absolute value of the inner product of fg is less equal than the norm of f times the norm of g. Okay, so I mean, this could be a complex norm, a number. You're taking the norm, so this is non-negative, or with this absolute value, and then you have less equal than the norm of one element times the norm of each other. So this is a very famous inequality. You probably saw it in your last quantum mechanics course, and this holds for spaces with inner product. And this is what helps us to let us guarantee that the inner product that we have above this one is finite for any elements in our L2 Hilbert space. Why? Because, well, we know that since these are elements of the L2 Hilbert space, the norm of f and the norm of g are both finite, so the product is finite. And because this is bounded by something that is finite, then this inner product is finite, at least in terms of its magnitude. So that's why this comes quite handy in order to have a well-defined inner product. Now, what we will do is, in order to represent a physical state, then we'll have something called the wave function, which must be normalized. Well, meaning that the norm of this should be 1, and according to our definition, then the norm squared, which is essentially this integral over AB of the norm squared, should be equal to 1. So this is so far in terms of the definition of the inner product and the norm in our Hilbert space of L2 functions over an interval to be defined later, depending on the problem. And the interesting thing, as we mentioned, is that the inner product in a Hilbert space lets you define angles between vectors. That's why Hilbert spaces are very interesting from the geometrical point of view. Because what will be more concerned in general in quantum mechanics is, well, the concept of orthogonality. So in the usual way that you have rectangles, you can have this orthogonality condition by having the inner product to be equal to 0. So this is an analogy with the finite dimensional vector spaces. And so orthogonality and this concept of basically being in rectangles is crucial in quantum mechanics for purposes we'll see very soon. And then you have, well, By definition, you can define an orthonormal set of functions as Fn with an index as a set for which basically if you take the inner product of Fn and Fm, then you have the Kronecker delta, meaning that this will be 1 if n is equal to m, or 0 if n is not equal to m. So this is important, so that way you can define the orthonormal sets. And later on, basically, we have another definition, which is what is a complete set of functions. A complete set of functions, let's say you have this index, again, going from 1 to infinity, is defined as one for which any function f of x in the Hilbert space can be expressed as a linear combination of elements in the set. So basically, this can represent any element in the Hilbert space by just choosing adequately the coefficients, Cn. And so that is why this set of functions is called complete, because it generates a space. And if you have also the property that this set is also orthonormal, then you can actually find the coefficients easily. Because if you take inner product of each element with the function of interest, given this property, well, you will have f of m, inner product with f being this representation. Then you remember that the inner product is linear in second argument, so you can take out the sum and the constants. And then you have the orthonormality property that was assumed at the very end. And therefore, you'll have the Dirac delta, and this will collapse by choosing only, basically, from all n's, only the one that is equal to m. And these coefficients, therefore, in the case where the complete set is also orthonormal, will give you the projections of the function f into each one of the functions fm. That's the idea. Okay, so far we have covered the inner product concept. Then we'll go to the matrix representations of Dirac vectors and of operators. So this, loosely speaking, I would say Ketambra vectors in quantum mechanics are basically the difference between vectors and functionals. So in a Hilbert space, which is infinite, the points in the space or these vectors in a space are basically functions, which are infinite dimensionals, and then the operators that act over these vectors and produce a number, say in the complex fields, is called a functional. But we will simply present a notation to represent these vectors and functionals and indicate what each one of these means. So before we delve into this, essentially, we have to mention what is the state of a system in quantum mechanics. And well, it's represented by a vector. This is the notation for the vector, so which is the Dirac Ket notation. You will see why it's called Ket in a second. So this is the Dirac notation, Ket notation for vectors in the Hilbert space. And this vector can be expressed with respect to different bases. So say, for example, if you want to represent basically in the position representation, so you have psi of xt, which represents the x component in the expansion of st in terms of the basis of position eigenfunctions. So what do we mean by this? Basically, you have your position representation, so you have position eigenfunctions, and if you take inner product of your state vector with the basis function corresponding to the position x, then you have psi of xt. Okay, so that is basically what we mean by this wave function in this position representation. Okay, so it's a projection in each one of the basis of position eigenfunctions. So again, yeah, we're performing the inner product with respect to the eigenfunctions x of the position operator. So they are eigenfunctions of this position operator because by definition, of course, being eigenfunction, if you take the position operator over this one, you get the associated position as eigenvalue. So again, this also lets you introduce the Dirac notation for functionals on the Hilbert space, and this is the point that I was making before. So before, what we had is a vector, which is going to be called a Ket vector in Dirac's notation. Now, how do we introduce the Bragg notation? basically, let's say that you fix, for example, in the inner product, the left argument. And so you have a function which is depending only on one element of the Hilbert space. So this maps vector of the Hilbert space into the complex numbers. And so it's a linear function, right? Because we assume the linearity in the second component, which is going to be the argument for this. And well, this is not important, but this linear function can be proved continuous by Kochizwar, not in the scope of the course at this point. And on the other hand, there is another theorem which is very important. This is more mathematical. You may or may not have seen this before, but this is the justification for what we will do in the second. There is a theorem called the Ris Representation Theorem that guarantees you that every continuous linear functional going from the Hilbert space to the complex numbers can be represented as an inner product C. So here, there's a difference. Here we assume that basically we're taking inner products of elements in the Hilbert with X. Now, this is more general because it's telling you that every continuous linear functional can find, well, vector C that such that if you basically take inner product with it, you get exactly the same outcome whenever for any vector in the Hilbert space. So this vector is unique, however, right? So then a continuous linear functional can be represented as basically being inner product with a vector, which is unique. And so again, for L, there is a unique linear, well, a unique vector Z in the Hilbert space, such that this continuous linear functional, when applied to vectors in the Hilbert space, is equal to taking inner product with C for any element in the Hilbert space. Again, every continuous linear functional can be represented as a given C and inner product with it, but there's a little bit of a difference. So, okay, you take inner product with this. However, this object mathematically is different. So, C with this other representation, not with this one, but with this one, this is an element of the continuous linear functionals from H to Z, okay? So it lives in that space of continuous linear functionals from the Hilbert space to the complex numbers. And there's a difference because this other element, which is the ket vector, is a vector in the Hilbert space. So again, the ket vector is a vector in the Hilbert space. The bra vector is a continuous linear functional. So mathematically, they're different. For the purposes, I mean, think about it. Basically, if you multiply any state vector with something like this, you get a number, right? So it's acting as a linear functional from the Hilbert to the complex. So that's the difference. And there is an important difference because, okay, in physics, you use Dirac notation. And then the Dirac notation, these elements are called bra vectors. So the notation, it gives away why we're doing that, right? I mean, if you have this is a bracket of Z inner product with S. And so S is the ket vector and Z is the bra vector in this case. So the notation is giving away what is the role. The ket vector is a vector, the bra vector is a functional. Never mind. Just trying to clarify the difference between these two objects mathematically, and which will be helpful for our physics studies. So again, the Dirac vector elements of the type Z with this bra thing are called bra vectors. And well, the Ris map identifying uniquely the linear functional with C. So again, let us identify uniquely continuous linear functionals, which vectors in the Hilbert space, okay, because they have the same effect. So this presents where bra vectors come from, also the reason of its notation, because this is a bra and this is a ket. Together they form a bracket, and you have the inner product between these two elements. And let's see. So there's also something important regarding this space of continuous linear functionals. So I said that the bra vector lives in that space of continuous linear functionals, where there's a name for that space. And it's called the dual of H, and it's denoted as H star. And it's also a vector space. It's intuitive in the sense that you have this identification of the linear functionals with another vector in the Hilbert space, but it has to be mentioned. So that's so much for basically the mathematical justification of this Dirac Ketambra notation. the discerning between vectors and functionals. Um, so we so far have presented, okay, how we can represent the state vector in terms of position eigenbasis. But that's not the only basis that we can represent the state vectors with. So we can also represent in terms of the momentum eigenfunctions, so which are of the form P, with eigenvalues belonging to the real numbers. I mean, I'm assuming like a 1D problem, essentially, where you have a momentum operator when applied to the eigenfunctions gives you a real number. And in the same way where the projection, or say the inner product between P and S, well, before you had X and S and it gave you psi, then it's going to give you, when you take inner product of P with S, this is phi of P and T. And so again, there are just different ways to represent the same state vector. The important thing is that you remember that this one is basically the projection of the state vector with this momentum eigenfunction. And that's why it's an argument of P and T. That's information that this carries, okay? Like for every P, it is the projection or inner product between the state vector S of T, because it's a function of time, and the momentum P. But again, there are just different ways to represent the same state vector. It can be different bases, can be position eigenfunctions, it can be momentum eigenfunctions. It depends on the problem, what is useful. And then also we have the concept of, well, yeah, I mean projections, etc. So let's say that you have an orthonormal basis, right? We're going to call it En. And so vectors can be represented by their components with respect to this basis. Okay, so we assume that it's a basis, so it generates a space and it has the orthonormal property. So this, okay, any state alpha is going to have this representation in terms of the orthonormal eigenbasis, and sorry, of the orthonormal basis. And the way to know what the disconfusions mean is basically by taking inner product in the same way we did for the previous example. So the vector alpha has this representation in terms of the orthonormal basis En, and these coefficients are basically the inner product of En with alpha. It is exactly justified the same way we did it for this, okay? But, well, we can also define operators. We're in a Hilbert space. We have already defined vectors, functionals with this ket vector and bra vector notation. And we can also define operators representing physical observables, and they will be considered linear transformations on the Hilbert space. So you start with a, say, vector alpha, you apply the linear operator Q that represents a physical observable, and you'll end up with vector beta. Of course, the linear operators have some properties that I will mention in a second. And the reason we are thinking of this as matrices is because, well, because you have an orthonormal basis with, let's say, an integer index, it's kind of like as if you had a vector, but okay, maybe the index will be infinite dimensional. But you can have a matrix representation for these operators just by orthonormality. Because, well, we have our own representation for beta, right? So it is, again, with coefficients Bn, where Bn are exactly this. And we also know that beta is Q applied to alpha, and it's a linear transformation. So, well, Q of alpha, if I plug in this formula for alpha, I will get this because Q is linear. So I decompose in terms of the sum and coefficients. And this lets me find some sort of matrix representation of Q in terms of this alpha basis. Thinking of it as if you had like a very long vector and you were to multiply with an infinite matrix Q, and then you'll end up with the infinite vector beta. This is the analogy, right? I mean, so you have matrices, but they might be of infinite dimension. So the way to know the form of these coefficients is basically, let's say I take inner product with N, okay? And the basis is orthonormal by assumption. So, okay, you'll have this. So let's say that you start over here. You take inner product with EM over here. So that will give you only the coefficient BM on this side. Then you're using this formula and you're taking inner product with Q of EM with the EM. And then we introduce this notation because basically the matrix elements QMN are going to be precisely this. So it's the inner product of EM with Q applied to EM. Okay, so operators representing observables, since they're linear, can be represented with respect to a given basis, like our orthonormal one, by the matrix elements as defined above. So this is the definition exactly. And these matrix elements indicate how components are transformed, of course. This is actually the same way you would define matrices and its components for finite dimensional spaces. So keep in mind that analogy because it might at least make things easier to understand, even if the matrix and the vectors are infinite dimensional. So if you have an orthonormal basis of ket vectors, En, so again, remember that this is the ket notation. So we can represent the identity operator by this. You probably saw this before, but it's easy to prove why this is essentially the identity matrix. It is because, okay, think of this. Let's apply this operator to a vector alpha. What is going to do? First, it's going to do inner product with the n. So that's the projection. Now, if you go back to the representation of alpha, what were the coefficients? The coefficients were essentially the inner products of En with alpha, which is precisely what we have here. And then we have the ENs as in here. So it's clear that by definition, this is equal to alpha. So what it's doing is basically projecting alpha in each one of the components of the orthonormal basis and then expanding the sum. And so that's by definition alpha. So it's acting exactly as identity. Okay. So you can also represent bra vectors in terms of this basis, which is called the dual basis. And it has a property. The property of the dual basis is that if you take inner product of, let's say, EM with EN, you'll have the delta MN. So, I mean, this we know by orthonormality. This is another way to represent the dual. And any ket vector can be represented by the orthonormal basis via this way. So this is something that we saw above, essentially. It's coming from here, okay? And in order to define the dual of alpha, or the representation of alpha in the space of continuous linear functionals, so basically it's alpha in its bra vector form instead of its ket vector form. So it's enough to define section over the elements of the orthonormal basis like this. So why is that? Well, this is coming basically from properties of the inner product. So it's a conjugate. Remember, we have that property. And so now the functional alpha is completely defined and we can represent it in terms of the dual basis as this. So we kind of like flipped in a way. The proof will be presented in a second. So we had this representation for alpha. Now for alpha as a ket vector, for a bra vector, we have this representation, and the proof is here. Let's say that we basically take inner product of this expression with the m. Okay, so what we will have is this vector inner product with the m. That's going to bring the Kronecker delta, sorry. And this will collapse in this element with n equal to em. So you'll have this. And so basically, this element where this vector matches alpha for all en. So these, you know, from this, then you compute this, then you have this equality, and therefore the bra expression of alpha is equal to this. And you just have to take conjugates of the coefficients originally, because if you remember the expression for alpha, alpha was, okay, this vector with this coefficient. Here having the dual alpha is basically the conjugate. So the summary of this short calculation is that if alpha has this expression in terms of a ket orthonormal basis, then its dual will have an equivalent expression in terms of the orthonormal dual basis with the coefficients just taking a complex conjugate. This is the summary. So that's so much for the matrix representation of operators. Trying to focus on what we will need later for the calculations. And well, we have, excuse me. So now we have the outer products of Ketambra vectors. So before, what we studied were inner products, Hilbert spaces and Ketambra vectors, basically how to define them. Now, if we have an orthonormal basis, En, we can, of course, in the Ket vector space, we can think of the inner product of an infinite dimensional Hilbert space as an extension of the dot product we know for vectors in finite dimensional space. So what does this mean? Well, we have alpha like this, beta like this. Alpha beta is the sum of, by using expansion, basically multiplying, well, using the dual, of course, with beta. And then by definition, this is Vn. So if you think inner product in finite dimensional vector spaces, it has a finite sum. This one is infinite because the index n is integer and, excuse me, it's infinite, but I mean, it has at least the same expression, even if the bound on the index is infinity. So we can make an analogy in the same way we did it for inner products between finite and infinite dimensional spaces. We can do it for the outer product. So let's define the outer product, let's say, of alpha and beta. So alpha with a ket, beta with a bra. And so this will be an operator that we will call A, capital A. So it's an operator in the Hilbert space such that if you take any element S in the Hilbert space, let's say that you apply this operator, what's going to do? Well, of course, it's going to multiply S with beta in the inner product setting. This is basically the component of S along beta. And then, well, this is multiplying the vector alpha. So it's capturing the component of S with respect to beta and then multiplying it by alpha, right? Again, the effect is to measure the projection of S along beta and then multiply by the vector alpha. So the outer product is a linear operator by linearity of the inner product in its second argument. That's clear because look, this is the form of the operator A, right? And so you have the inner product and then you have the linearity properties over here because alpha and beta are fixed, okay? Then if you have an orthonormal basis, then we can make the analogy with outer products of finite dimensional spaces. Yeah, the same way we have this expression, right? And so the easiest way is, because it's a linear operator, to find the matrix representation in terms of the orthonormal basis as we did before, right? Over here with the, well, in the case of general physical operators, which of course, in addition of being linear, they are also assumed to be Hermitian, but that's something that you already know in your course. That's why perhaps I'm not pointing that out so stressfully, but this is important for calculations. So, well, we're here. So we'll find its matrix representation in terms of the orthonormal basis, as we did before. So let's say we have the basis En, right? And so we have AMN, the same matrix representation by definition. If you remember for Q, we had these definitions of the matrix elements. So we will do the same exactly. So AMN, it's En, then the operator sandwiched in here, which is by definition outer product alpha beta, and then En. So if we do that, well, this is the natural definition of the coefficient of alpha and the other basis. Then this is beta inner product En, which is the complex conjugate of Bn. And so with this expression, it's kind of clear what is the effect of A in the elements of the well, of the basis. So this is analogous to the outer product of a column vector with a row vector. Of course, the column vectors are kets, the row vectors are bra. And they generate a matrix by multiplying the component with the conjugate Bn. So it's a linear operator of rank 1. So that's clear. It's the same way you have the outer product for finite dimensional matrices, but in this case, it's for infinite dimensional. You can picture yourself basically taking infinite dimensional matrices and having the same thing. However, with the important point that Bn is being taken as complex conjugate. Now, There's a simpler case, what happens when you take beta equal to alpha, right? And so basically what that is doing is simply projecting the argument along alpha. And that is a projector operator onto the subspace, which is of dimension 1, spanned by alpha. Okay, imagine just what we would get here. Basically, okay, if beta was equal to alpha, you will have the component of S with alpha and then expanding in that direction with this ket vector. Okay, so we can actually go back to one of the points that we mentioned before, that the identity operator is basically doing this, but for each one of the directions or the components in the orthonormal eigenbasis. Because let's say you project with any vector in the Hilbert space, for each one of the ends, okay, you take inner product, so you get the projection or the component, and then you expand in that direction, and then you add the sum. So you're adding over all possible directions. So again, the identity operator is simply obtaining the projection along each of the basis vectors and then adding them to recover the initial vector argument. That's why it's the identity which we have proved already before that it behaves like that. Now, this expression of the identity doesn't need the assumption of having countable bases. So here we're assuming kind of countable because the index is integer. So this can be extended to the case where the basis is not countable, but rather has the cardinality of the real numbers for the case of position or momentum uh, representations. So the real numbers in that case will have a continuous index. And so for that representation in position or momentum eigenstates, we simply replace the same way you go from discrete to continuous. So you replace the sum by an integral, and you can write the identity operator as this. So this is the same representation. The identity is basically adding over all possible states. This will project, and this will expand in terms of that direction, and the same thing for the moment. But notice the analogy between this countable, I guess, infinite but discrete case versus discontinuous. You just replace the sum with an integral, and of course you need an element of integration, which is dx or dp. So regarding, okay, regarding position and momentum operators in each one of those representations, so we remember that we have this, right? Okay, we can represent the identity. So now we will explore what is the form of a state vector in those representations, okay? So let's say that you have, or you're given a state vector as of time, so t is time, and it can be represented in any of these bases by the following way. So, okay, this is, remember this part, right? So you have the state vector, then this is just identity, so it's gonna be, again, the state vector. If you do that, you already have a name for basically the inner product of x with s, which is psi. And then you have this term over here, and this is basically an integral over dx of psi times the vector x, which is part of the basis of um, position eigenfunctions. So again, this is just reminding you the formula that we had before, where psi of x and time is the inner product of x with the state vector s as a function of time. And the same calculation can be performed for, well, in the momentum representation, where you have the identity operator in terms of momentum eigenfunctions. You will project, you will expand. This sum is performed over the continuous index. That's why you need an integral and then dp. And then phi of p of time is basically the inner product between p and s. So the position space wave function defined like this is a component of the state vector s along x, as we saw before, and the momentum space wave function, again, is a component of the state vector s along p. And these are the position and momentum representations of the state vector, right? Because this is equal to s of t. So it's this equal to this equal to this. Depending on each representation, that might be convenient for your problem. So given that both position and momentum are physical observables, we will study now the form of the Hermitian operators in both representations. Okay, so I mean, for of course, if you're in the position representation, the position operator is trivial, and likewise, if you're in the momentum representation, the momentum operator is very easy to find. It's just multiplying, right? But by the respective momentum, but it might not be as simple if you are in the other. What is the form of the position operator in the momentum representation? And what is the form of the momentum operator in the position representation? That's the thing to basically study now. Now, operators can be expressed in a given representation by taking the inner product with a corresponding basis vector. Say, for example, for the position operator x, we have this, right? So we have the state, we have the operator, and then we have an element of the position eigenfunctions. So this has the property of being Hermitian, and you can pass it to the other side. And then, well, basically this will take out the element x, because you'll get an x here, you can take it out. It's a real number, so there is no effect in terms of the complex conjugation. And then you have again x with s, which was psi, right? So what is clear from here is that x is equal to basically multiplying by x in the position representation. And there's an analogous calculation of the momentum operator in its own representation, which is showing why this case is easy. So you have the momentum operator, then sandwich in the inner product between P and S. So you use the Hermitian properties, then you apply the operator, you'll take a P out, it's real, so there is no effect in the complex conjugation for this quantity. And then you have P times phi by definition, right? So these are the easy cases, of course. Not so easy is the other ones, what happens if you're in the other representation, but you have studied part of this material before. So I'm just going to try to remind this and give you some arguments into why this holds. So the momentum operator has the form in the position representation of P equal to minus I h bar partial with respect to x. So just to give some intuition into why this happens, right? Let's say that you have a free particle with a position space wave function, which is psi of x in time. So we know that the free particle is basically behaving like a wave, where it's e to the I kx minus omega t. So sorry, I may have a typo here. Yeah, sorry. And yeah, so we're going to substitute in here. Well, we know the Planck's laws, basically P equal to h bar k and energy equal to h bar omega. So that's why we did this substitution. And then if you apply, well, actually what I'm trying to prove is that it has this form. So, well, we have P times the wave function in the position space, which had this form, of course. Then how could you retrieve P from this state or this function representation? Well, if you actually took partial with respect to x of this function and then multiplied by minus I h bar, you would get P. Because, okay, taking derivative, you will get, well, it's the partial derivative with respect to x, you will have IP divided by h bar. Then you multiply by h bar, you take out the ratio, then you'll have minus I squared, which is equal to 1, and you just get yourself P. So perhaps we should have started this way, but I want to show intuitively why the effect of this momentum operator for a free particle, which is getting P, is precisely by this minus I h bar partial x. So perhaps the formal proof would go in this direction, but this makes it makes the calculation very intuitive into why we get what we get. So this, of course, was a calculation just for a free particle. So this points out to the fact that the eigenfunctions of the momentum operator in the position representation are of the form, well, if you're taking a product of x with p, so again, you'll have the representation as a function of x, and so you have the wave particle form as you had before, ap e to the ipx over h bar. So this is looking the same way as we had over here with respect only to the x part. So, well, if you were to follow the computations, you have, this is the simple case, of course, P operator applied to its eigenfunctions, you look at the P, then you can do this calculation in the same fashion as we did before, and we have the form of the operator over here. And then you have the inner product between position and momentum eigenfunctions, which is like this, and by definition of P. So just thinking about this, okay, this will be the operator of momentum in the position representation, which is what we are on right now. And okay, here we have the momentum operator applied to this function. This has the easy effect because it's basically representation of eigenfunctions of the momentum operator in the position representation. You should just retrieve P. And well, all this mathematical expression is trying to prove that you have basically a dpq for the function under concern. Of course, we already know the result, but it's trying to kind of like present why this inner product between x and p has this form. Okay, so you'll have that since you have this dpq, that's why you have the exponential like EI, right? So you could pass this other stuff to the other side, and then partial derivative with respect to x of fp of x is p divided by minus I h bar. So that gives you the form. Anyways, you probably are familiar with many of these results. And then you have, well, it's not quite a normalization constant because you probably know that for free particles, they are not normalized. You basically have a wave oscillating in space, and well, if you compute the amplitude over the whole real interval, that's not going to be finite. But since you don't have, formally speaking, actual orthonormality, you have something that is kind of like a second best thing or a remedy, which is called Dirac Orthonormality, which is that you want is some sort of Dirac delta behavior between two different momentum eigenfunctions. So I'm going to give the summary of the idea. So you have inner product between two different momentum eigenfunctions, p and p prime. And then you want this to be equal essentially to a Dirac delta of p minus p prime. I will go into the details of the calculation, but I'm trying to present that essentially you'll get this, and you want this coefficient to be 1, okay? So let's perform the calculation. So if you were to do this, you basically insert the identity operator over here. Then what you will have is, well, passing things inside are projections of p with x and x with p prime. And this, by definition, using this formula, is f star p and then f p prime. And this, well, if you think about it, okay, we'll have this one or its equivalent conjugate, etc. So you can add these two over here with properties of the exponential, and then you'll have AP prime. So you can take them out, and then the fact that this is equal to 2 pi h bar delta of p minus p prime, it's a mathematics result. So what we're trying to say is that we're missing to define this coefficient. It's sufficient to choose AP equal to 1 over square root of 2 pi h bar for all the p's. So in principle, this could depend on p, but it's not going to be the case. If you make this choosing, basically you get what you want, which is that the inner product of two different momentum eigenfunctions will get you the Dirac delta. So this is the second best in terms of normalizations. And now you have the definition of the inner product between position and momentum eigenfunctions, which is this function, which is the exponential of IPX over h bar divided by square root of 2 pi h bar. So, well, you can now transform the position space wave function to the momentum space representation. So, which is something that is going to be quite useful, right? Depends on which representation you want to be. But let's say you have it in the position space and you want the momentum space one. So you know by definition that psi of x and time is the inner product of x with s. And then you want the equivalent one, which is phi of p and t, which is inner product with p and the state vector s of t. And then this can be retrieved by making a smart choice of the identity operator in this way. So um, phi of p and t, the inner product of p with s, insert identity operator over here. Then you have, well, you can identify, first of all, this projection. Second, you'll take out the integral and you'll have px over here. Then this is already known. This is psi. And then you'll make use of the formula that you just found, right? Because, well, you'll have the conjugate of this, of course. That's why you get the minus over here. And, well, the coefficient is real, so that's not an issue. You just substitute, and then this gives you the formula for um, phi of p and t in terms of psi of x and time by this integral transformation. So again, we made use of this that we just discovered a little bit ago. And to try to not lose ourselves in the forest, essentially the relation between position and momentum spaces is basically the one of Fourier spaces. So you can go between one and the other via a Fourier transform, which is exactly what we have here. If this is the first time you see it, maybe it's not evident, but if you have seen it before, you already know the story. So we are in a physics theory where things are waves, and in that space, you can go basically to the frequency space, which is the momentum space, except for a constant. But, well, again, the momentum space representation of the wave function. So there is a factor of h bar that might not make things completely clean, but it's the Fourier transform of the position space representation of the wave function. What we have above is basically a Fourier transform. So how can we go back, let's say, from momentum to position again? Well, we'll use an inverse Fourier transform, right? So since we know that this is a Fourier transform, we apply the inverse in the same way, and we will get, again, psi. And, well, because this was minus, here is plus, and we have the factor to basically go back adequately to the original function. And so what we're interested now is on the form of the position operator in the momentum representation. So for how the momentum looks like in the position representation, I basically made an argument of the free particle, and you have already studied that. So it's kind of intuitive what happens. In a free particle case, you only have to derive with respect to x and basically multiply by something adequate to retrieve the momentum of the free particle. But in the other, perhaps it's not that evident, although the connection via Fourier transforms between position and momentum might give you a hint on why we'll get the following result. But you can do, again, this technique of inserting the identity operator. So, okay, I want to retrieve the position operator in the momentum representation. So I have a state S, I have the vector P, well, bra vector. Then I have the position. So I also insert identity operator over here. So this is operator times identity is operator. We have the same thing. Then I start to basically project, right? So this is equal to psi. Then I pass integrals outside. I put the P in projection with X. And then I'll have the effect. Well, I have to apply this one first, right? So actually what will happen is that I apply X operator to this X eigenfunction. So that's how I get the X over here. And then I need the formula of how psi looks in terms of phi. Wait. No, I'm not there yet. I need to make a step. Sorry. No, what I need in this step is basically the formula for P inner product with X, which is this one. We got the actual formula over here, which is what I'm going to substitute in here. Right. So I do that. I have P inner product with X, so that's why I had the minus over here. And so I can take some factors out. Well, then I have the e to the minus over here as well. And then what is the effect of basically getting x from here? So this would be the same as if I were applying partial derivative with respect to p. Uh, so I would get the x out. Of course, I need some normalizing factors over here. That's why I get the IH bar. And now by this, I'm identifying part of the equation that I had over here, right? Because had dx e to the minus IPX divided by h bar divided by 2 pi h bar and then psi. So that's exactly all this object is precisely phi of p and time. So this is equivalent of taking partial derivative with respect to p of phi of p and time. And this is therefore IH bar. By definition, this is the projection of S with P. And the same way we identified operators before, this is how we identify, therefore, that our operator of interest over here is basically IH bar partial with respect to P. So this is the representation of the position operator in the momentum space representation. Notice it's not so surprising if you look at the form of the momentum in the position space, right? Of course, you have different partials and the minus, but with the Fourier connection, it's kind of intuitive why that happens. So that's the information that you need, and later on we'll use this. So the last part to analyze is how Schrodinger equation looks like in the position and momentum representations. So the Schrodinger equation establishes the equivalence between the actions of the Hamiltonian operator and the energy operator. So that is kind of like the crucial thing, right? So the Hamiltonian is the same as the energy operator. The energy operator, well, the effects over the space. And it's not that they are equal as operators, but Schrodinger equation is that the fact that this operator is going to be equal to the energy operator. Okay. The energy operator is IH bar partial with respect to time. You saw that before. So Hamiltonian operator is basically using the classical Hamiltonian. We will plug in for the momentum in the position representation, for example, the representation of the momentum, and we'll use that as the quantum operator. So the Hamiltonian in the classical case was the kinetic energy plus the potential. And well, before we make any choices of the space or representation, so far so good we're here, right? This is energy operator, Hamiltonian operator, and this is Schrodinger's equation. Now, since the kinetic energy depends on the momentum operator here, and the potential could depend on the position operator, may or may not, depends how simple or complicated your problem is, it's clear that the Schrodinger equation will have a different form of the position and momentum representation. Well, yeah, that's clear. You might be more familiar, or you might use more frequently the position representation, but you can have a form in the momentum. It's not as explored, and I'll tell why. But first things first, in the position representation, we know that P has this form, minus IH bar partial X. So P squared is a composition of P with P. So that's why you'll get minus H bar squared partial with respect to X squared. And then let's assume for the moment that the potential is a function of X, right? So the way Schrodinger equation would look is using this plus this. You would have IH bar partial T, the projection of X with S. Then you'll have X projecting with this Hamiltonian operator, which is going to use actually this with S. So what you'll have is the Schrodinger equation in the position representation is simply IH bar partial of psi with respect to time, by definition of this. It's going to be, then you plug in this operator, then you'll have minus H bar squared over 2m partial square with respect to X plus B of X psi. So again, we're using this, this equal to this over here. So, well, so there is an equivalent representation in the momentum space of the Schrodinger equation. So the same way, I mean, there is something to learn, right? In the position representation, we substitute momentum by the known operator. We're going to do the same over here. So this would be our starting point, right? And then we would basically invoke the projection with respect to P. Then we'll have P, then sandwich the Hamiltonian operator. And then the thing we're gonna substitute is basically IH bar instead of X, okay? So, well, in principle, we could do that. B can be a very complicated function. If we were lucky enough that B of X can be expanded as a power series in X, then basically what you do is the same, just as power series, uh, substituting for X, the operator IH bar partial time. So there is a problem with that though. And think about it for a second, because let's say that we would have a power series for B in terms of X, right? So in general, that power series will contain terms of all orders of X, meaning that it will be infinite. And so that will be reflected because the same way you would have X to the fourth, X to the seventh, etc., or X to the n with n going to infinity and not dying in general. So what you'll have is that you'll have derivatives of higher and higher degree in terms of momentum. And so that's not so mathematically easy to analyze. We're familiar, of course, with PDEs of first order, second order, maybe even third order, but infinite order sounds quite complicated to manage. So what we would get by using this is a PDE of infinite order in X. And well, that would be actually in P. Because, okay, the series is infinite in X, but the derivatives on P will appear. And yeah, that would be the not nice thing. So the last term can be expressed in a more convenient way if we apply a Fourier transform to the Schrodinger equation. So the summary is that we already know the connection between position and momentum spaces via Fourier transform. So it might be more helpful to apply a Fourier transform to the equation that we already know is the Schrodinger equation in the position space to get a similar equation for the function of P and T. Okay, so that's why we're doing that. So again, if we apply a Fourier transform to the Schrodinger equation in position space to obtain an integral equation, then we'll get an equivalent expression for the Schrodinger in the momentum representation. So let's say that we do that, right? So we remember the connection. Essentially, this is the connection where we have the Fourier transform and its inverse. We'll use this one. We have Schrodinger equation over here. Let's apply that Fourier transform over here in this one. So you apply Fourier transform to this operator and to this part. And well, I'm going to skip a little bit of the calculations, but do not lose yourself in the forest. So you have this expression. Then let's say that you integrate by parts twice this term. So, and this is the nice thing, in Fourier space, there's an equivalence between the partial derivatives with respect to X, with of course a factor, and the momentum representation. So what will happen, well, first of all, you can basically take out the time operator over here, because there is no effect since you're taking an integral in X. Everything else is not time dependent, like the exponential or the constants. So that's one step ahead. The second one is that essentially, well, this, by using this identity, you'll retrieve, no, this is a next step in a second. But first you take out the constant terms, then you prepare yourself to apply this identity later. Then basically you have the potential and sandwich in this Fourier transform. This is by definition, of course, the momentum representation of the wave function by Fourier transform of the position one, which is why we get this. Then again, I told I was going to use this property twice, which is why I get the p squared over here. It's coming out from these two partial derivatives by integrating by parts twice, this second term. And then we have this result. So, well, this perhaps can be manipulated a little bit. Not so much, but you'll see. So what we will do is to use convolutions. So this term remains the same, this other likewise. In this one, basically we are using a convolution theorem in order to express this same integral as this, okay? So we have two integrals. We have the b up to the e minus I p prime x over h bar. And then by using convolution, we have this. Okay. So this is nice. So this is a nicer expression for the Schrodinger equation in momentum space. And of course, what is happening is that there is a Fourier transform of the potential over here if you identify the expression of Fourier transforms in this part. And there is an identity in order to pass from here to here, which is the one that we proved before, how to get the Dirac delta normalization sort of for momentum functions. And well, this would look nice, but it's a little bit complicated and it's not that convenient to use. In fact, there is a book by Saxon where there is the following remark indicated on the usefulness of this Schrodinger equation in momentum space, which is that unless the potential is a very special function, the momentum space equation is way more complicated than in the position space. And the reason for that complication in momentum space compared to how easy it is in the, well, to the simplicity of the momentum space equations for free particle, but that's not the case because we have a potential in this case, is that the momentum is no longer a constant of motion. So you have external forces and the state function will contain a broad mixture of pure momentum states. And this mixing is represented by the integral in the equation. So the summary of this observation is that basically, except you are in the case of the free particle, this is not that much of a convenient expression, even though we use Fourier transforms and get convolution to get this cool expression. But I guess the only place where something like this Schrodinger equation in momentum space would be recommended to be used would be for the case of the free particle problem. In general, perhaps it won't be useful, but at least I think it's important for you to know this form. You'll have a problem related to this for, of course, the case of the free particle. But yeah, this is the quick summary of what you saw in your course last semester. Perhaps there are some things a little bit new or more mathematical, but it's trying to basically give you a broad scope and to highlight the important part of your previous course. So if you want more references, you can consult these ones, which are also in the lecture notes that I'm about to post. And of course, the Griffiths one is the main one. All the others are perhaps for some mathematical complementation to this. And the Saxon is more focused on the Schrodinger in momentum space. But well, hopefully this will help to get gears started. And if there's any question, just let me know either from the material or the homework that I will post on Friday. So hope you like the first lecture and see you very, very soon.